Hi, so the first few lectures are going to be centered around Euler's theorem, which is one of the oldest theorems in topology, and I think will be a good introduction to the course. So Euler's theorem is about polyhedra. So let me give you a definition. A polyhedron is a union of polygons in free space that are glued together in sort of a nice way. So let me draw some pictures to first give you the idea. So here are some polyhedra, which likely look familiar. So you just have some collection of polygons, and they're glued in some way. So, okay, what is this niceness condition? So we want them to be glued so that, first of all, each edge is in exactly 2 polygons. So we don't want to see this picture around an edge. Here you have 3 triangles coming together. That's not allowed. And then the second condition is that about the local picture around a vertex. So the local picture around a vertex should look like this. So should be collection of polygons which are consecutive ones meet in an edge. So so here QI and QI plus 1, these are polygons, so there's some other sides which I'm not drawing, share an edge. So the type of thing this excludes, so here's an example of a non-example. So if you take 2 of these shapes, this is a tetrahedron, and you glue these along a point, then around this vertex, the picture is not like the picture here. So this is also not allowed. Okay. Right, so part of the basic data of a polyhedron is the number of vertices, edges, and faces. So so for a polyhedron P, will denote V, E, and F, the number of vertices, edges, and faces. Faces just being the polygons. Okay, so now let me tell you a curious thing about these examples that I've drawn here. So for the examples above, V minus E plus F is equal to 2. So let's see this. So here, there are 4 vertices, 6 edges, and 4 faces. And so we get 2. For the cube, we have 8 vertices. There are 12 edges and 6 faces. So again, we get 2. And in the last example, see if I can draw it in a way that we can tell what's going on and count. So V minus E plus F, there are 5 vertices in the front, 5 in the back, so that's 10. The edges, 5, 5, and 5, so 15. And the faces, 2 from the front and back and 5 all around, so that's 7. So again, we get 2. So given this, we might ask the following question. Well, is this true for every polyhedron? So is V plus E, V minus E plus F equal to for every polyhedron? So we've observed this pattern for these particular examples, and the question is there something special about these examples, or is this just something that's always true about polyhedra? Okay, so let me move the question to the top and say something about it. Turns out the answer is no, and it's not so hard to see why. So for example, well, a silly example is to take P a disjoint union of 2 of the examples. So the number of vertices, edges, and faces just adds. So here you get, well, you'll get 4. So, I mean, you have P1 and P2. I guess one way we could write this is, well, okay, yeah, let me just, so here you get 4. You might say, well, this is sort of a silly example because this example is just, you're taking, this polyhedron is a union of 2 polyhedra. So maybe we should exclude that sort of thing. But here's another example where it doesn't work, where it's not a union of 2 polyhedra. So this example, we start with a cube, and we're going to drill out a tube from this cube. So so I'm going to drill out some sort of rectangular prism from inside of here all the way down to the bottom face. I hope this picture makes some sense. So let's see how many, what the count is for this example. So the vertices, we have vertices here and here. So there's 8 on the top and 8 on the bottom. So we have 16. Edges, so for edges, I guess technically I should, this top face is not a polyhedron, so I should divide this. Well, one way to fix that is to just divide like this. Same on the bottom. So, okay, so now let's count edges. There are 12 on the top, 12 also on the bottom, and then around in the middle, there are 4 plus 4, so 8. So that's 32, and I should be subtracting, minus 32. And then faces, 4 on the top, 4 on the bottom, 8, and then around the sides we have 4 outside here and then 4 inside. So that is 16. So in total we get v minus e plus f is 0. Okay. Right, so now let me tell you what Euler's theorem says. So this dates back to 1700s. So let's take P, a polyhedron, and suppose that, so 2 things. First, any 2 vertices of P are connected by a sequence of edges. That's the first condition. The second condition is any polygonal loop separates P into 2 pieces. And so then the conclusion is, so if these 2 properties, P has these 2 properties, so then V minus E plus F is 2 for P. So let me point out that these 2 properties, 1 and 2, exclude the 2 examples that we saw on this previous page. So the example P is a union of a tetrahedron and a cube. This fails 1. So here you have 2 vertices that are not connected by a sequence of edges. And P, the other example, which let me give this a name. Let me call this the torus polyhedron, because topologically this example is a torus, which is like the surface of a donut. For P, this torus polyhedron, this fails property 2. So you can see this, well, maybe it's easiest to see this in this picture. So the claim is that there is a loop which does not separate P into 2 pieces. And well, here is such an example. If you cut along this loop, you still just have 1 piece. And in this picture, you can draw it polygonally, sort of like this. Okay. So the theorem says, well, if P has these properties, then you can conclude that the V minus E plus F is 2. So let me make a comment about, so this is a cool theorem. Yeah, so let me give you an example, a concrete example of how you can use this theorem. So I was searching around my apartment for a polyhedron, and I found this, which is a pot for plants, I think. And well, it's clearly made up of polygons, which are glued together. Ignore the fact that it's 3D. I'm just thinking about the surface. And it's not so hard to check the conditions of the theorem for this polyhedron. So topologically, this polyhedron looks like, well, okay, so you have sort of these thin, let me draw in black. Have these thin rectangles. This is kind of the top here, these thin pieces. And then, well, there's a square down here that connects to. And then there's sort of an inside part of the polyhedron, which I'm going to draw not inside. I mean, counting this v minus e plus f, it doesn't really matter whether I draw it sort of going inside or coming up. So here's this pot polyhedron. And well, okay, you can just check. Look, any two vertices are connected by the sequence of edges. Okay, fine. I mean, you give me two vertices, I'll find some sequence of edges between them. And then any polygonal loop separates P into two pieces. So, well, you can just look at all the different loops. I don't know, maybe here's one, goes up around like this. And indeed, well, it separates into two pieces. You have sort of this piece here, which includes some of this back face here. And then there's this part here, which includes some of the back face there. So, okay, so the theorem's true for this example, or so these assumptions are satisfied by this example. And so then we automatically know that v minus e plus f is 2 for this example, without having to do any counting of vertices, edges, and faces. So one thing you might ask is, well, I mean, back on this slide when I talked about this curious fact, you could say, well, why did you choose v minus e plus f? You know, why not v plus e plus f, for example? And well, this Euler's theorem gives you some, well, it's maybe, yeah, I mean, this theorem, it's saying that v minus e plus f knows something about the topology of P. These conditions here, these are some topological conditions. Later, we'll see that we'll have some terminology to say that this is, what we'll say is that this P is connected, and this condition is what we'll later call simply connected. And these are topological properties of a space or a polyhedron in this case. And this quantity v minus e plus f knows something about the topological properties of the polyhedron. So let me give some terminology. Maybe I'll fit it here. So v minus e plus f will denote as chi of P. This is the Euler number, or also known as the Euler characteristic. Of P. And so, okay, so what I was trying to say before is it knows something about that. It's telling you something about the topology of P. I mean, topologically, like these examples here are topologically like a sphere, whereas the torus polyhedron is topologically like a torus. And the fact that the torus and the sphere are different spaces is reflected in the fact that they have different values for this V minus E plus F. Okay. Okay, so now I want to switch gears and talk about something a little bit different. So the goal over the next couple lectures is to prove Euler's theorem. And for that, we're going to need to know a little bit about graphs and properties of graphs. So a graph roughly is a one-dimensional polyhedron. So let me draw some pictures. It might look something like this, or something like this. So in a graph, you have vertices, which for us graphs will always be finite. So this will be a finite set. So not really drawing them in here, but here are the vertices. And you have edges, which connect distinct pairs of vertices. Okay, so this is what a graph is. One way to get a graph is from a polyhedron. So if P is a polyhedron, then you can get a graph by taking P and removing all of its faces. It's two-dimensional polyhedron, or the interior of them. So for example, for P, the cube, well, we could also think about this as a graph by just ignoring the faces. So maybe I'll just draw it a little bit differently. The associated graph could draw like this. Okay, so a couple of terminology about graphs. So we say that G is connected if any two vertices are connected or differ by a sequence of edges. So for example, like this graph here is connected, but this graph here is not connected. Okay, another definition. So we say a connected graph G is a tree, if removing any edge disconnects G. So for example, let's take this graph here. So this graph is not a tree. Because, well, okay, so we just need to find an edge that if you remove it, the graph is still connected. So let's take E, this edge. So this is not a tree because G minus E, which is this graph, is connected. Connected. Okay. Right, so as it will turn out, trees are going to be quite important to understand in the proof of Euler's theorem, and actually they're going to come up quite frequently in the course. So I want to prove a couple of things about trees in the rest of today. So the first, I think I'm just going to start a new page. No, let me stay here for now. So let's say, okay, so let's take G, a connected graph. So then G is a tree if and only if any loop in G backtracks. So to illustrate, well, let me work in this example. So here's, this graph is not a tree, which according to the lemma means there should be some non-backtracking loop. And that's what I'm drawing here. So this union of edges gives a loop, which doesn't backtrack. On the other hand, right, so a loop is a sequence of edges which starts at some vertex and then comes back to that same vertex. And if you're in a tree, then there's just no way to find such a loop. I mean, if you're in a tree and you start along some sequence of edges and then you want to return back to the edge that you started at, you have to at some point turn around. So this is what the lemma is saying. Okay, so let's prove this. I think I'm going to, let's get a new page and clean up a little bit. I want to keep the definition up and the statement of the lemma. My eraser's being slow. All right. Okay, so proof. So this is an if and only if statement. We need to prove both directions, both implications. Start with the forward direction. And what we're going to do is to prove the contrapositive. which is going to be easier than proving the original statement as stated. Not a contradiction, contrapositive. Which is to say that if G has a non-backtracking loop, then this implies that that G is not a tree. Okay, so let's prove this. So let me so let me see if I can do it this way. So this is what we're starting to assume, and at the end of the day, we want to get to here. Right. So let me just put this down here. Oh, let's see if this works. See if I can fill in the rest with the argument. So suppose G has a non-backtracking loop. Let's draw it. So we have some loop in G which doesn't backtrack. So this is in G. And let's pick an edge on this loop. Call it E. So the claim is that G minus E is connected. Well, if we prove this claim, then we're done. So that will imply that G is not a tree, since in a tree, removing any edge gives you a disconnected graph. So really it suffices just to prove this claim. So, all right, so let's do that. So proof of claim. So we want to show G minus E is connected. So let's fix vertices. Of G minus E. And we want a sequence of edges in G minus E connecting them. Okay, so let me continue the picture here. So we have some P and some Q, and we want a sequence of edges in G minus E connecting them. So the first observation is let's see, I'm out of space here. Let me just get a little bit more space, duplicate this, and just going to remove the definition and try to keep the rest. Okay, that's not what I want. This thing is being, wow. All right, let's see if I can wrestle this thing. Just stop. My goodness. This is not responding to me very well, sorry. Okay, and I think my picture is going to be blocking some of the text here. Sorry, bear with me. Still getting used to how Zoom works. I hope this will all be visible. Okay, so what can we say? So we want a sequence of edges in G minus E connecting P and Q. So we know there's a sequence in G because G is connected. That's the assumption at the top. So now there's two cases. So the case one is this sequence of edges contains E, or it doesn't contain E. Let's say case one is it doesn't contain E. So then we're done, because then the sequence of edges is in G minus E. Okay, and now case two, really pushing the limits of what you can fit on a page here, is the sequence contains E. Okay, well now, okay, so now the picture is we have some sequence of edges and it goes through E from P to Q. And well, this case isn't so bad, because what we do is we just replace E by, well, we have this loop that we found in the graph. And so there's this other way around if we don't want to go through E, call that gamma. So just replace E by gamma to get a new sequence, or a new sequence of edges, which is going to avoid E. So this will be in G minus E. Okay, so that's the proof of the claim, and that does the forward direction. Okay, so now let's prove the other direction. I'm going to duplicate this page again, and then just erase the argument that we did so far. Okay. So now let's do the backwards direction. And again, we're going to prove the contrapositive. Which is to say that, let's see, if G is not a tree, we want to start assuming that, and eventually conclude that there exists a non-backtracking loop in G. Okay, so this is the structure of the argument. Now let's fill in the details. So G is not a tree. This means that there exists an edge E, so that G minus E is connected. So let's let P and Q be the vertices of E. So we have E and P and Q. So G minus E is connected means there's a path, or a sequence of edges. That's what I mean by a path in G minus E connecting, all right, let me say just from P to Q. Okay, so who knows what it looks like, but there's some path, and it's in the complement of E let me call it gamma, path gamma. And moreover, well, we can assume that it's non-backtracking. I mean, as a little exercise for you, if there's a path between 2 points, there's a non-backtracking one. You can sort of simplify it to make it non-backtracking if it is backtracking. Okay, but now we're done. So then gamma union E, well, look, we just found a non-backtracking loop. Non-backtracking. Backtracking loop in G. Okay, which is this statement. So that's the lemma. Okay, so this is a useful characterization of what it means to be a tree. Trees don't have any loops. Okay, so so there's one more thing I want to prove about trees. But before that, let me state one other thing. Let me mention one exercise, which is going to be part of homework 1. And that's that, so for any graph, G, there exists a tree, T and G, that contains every edge, or every vertex. Of G. So for example, take this graph from before. And actually, let me, before I draw any more on it, double it. I'm gonna want a second copy. So the claim is just that there's some subgraph, which is a tree, doesn't have any loops, and it visits every vertex. Let's see. So that works. And a remark is that T is usually not unique, which is why I have the second copy here. So, well, a given graph might have many possible T's with this property. So let's see if I can draw a different one. I mean, there's lots of choices. Let's do something like this. Yeah, so that goes through every vertex. That looks fine. Yeah. Okay, so this fact is something you'll prove in homework, and will come up when we talk about the proof of Euler's theorem next time. Okay, so right, last thing I want to do today is the following lemma. I'm gonna put it on a new page. So it's about trees. So T is a tree with V vertices and E edges. So then V minus E is always equal to 1, no matter what tree we choose. So you can think about this as the version of Euler's theorem, but for trees. So let's prove this. Proof is not so bad. So first, well, okay, the way this is going to work is we're going to induct on the number of edges. Which is E. So the base case is E is 1, and well, there aren't many trees with exactly one edge. And well, this is all there is. This is the only possibility. So so T looks like this. If we were talking about graphs with only one edge, then there'd be other possibilities because you could have some other vertices floating around here, but trees are connected. So a connected tree with one edge just has 2 vertices and 1 edge. So then the Euler number is 2 minus 1 is 1. Okay. So that's the base case. Now the induction hypothesis, let's assume, assume that the lemma holds for trees. Sorry, let's fix E and assume the lemma holds for trees with less than E edges. And and then we fix T with exactly E edges. And we'll prove the lemma for T. And the way we do that is pick any edge, E in T. T is a tree, so T minus E we can write as a union of 2 graphs, which are actually, well, it's T minus E is disconnected, so that's, T is a tree, so that's what happens. And so the picture is something like this. So we have, here's T, we have this edge E, and right, so if we remove E, we get 2 new trees, T1, T2. And well, now let's compute. So I always need just a little bit more space. Let's see if I can get it. Okay, so now let's compute. So VT minus VE, or ET, using the subscript to indicate that we're talking about vertices of T and edges, number of edges of T, because we're gonna rewrite this as, well, the vertices of T are all either in T1 or in T2. So this is the vertices of T1 plus the vertices of T2 minus the edges of T. Well, there are the edges of T1 or the edges of T2, but that doesn't cover all of them because there's also E. But that's it. And so we can rewrite this. This is VT1 minus ET1 plus VT2 minus ET2 minus 1. Okay, so now we're just about done because, so the induction hypothesis applies, this is the Euler number for T1, and the induction hypothesis says that this is 1. T1 has fewer edges because it doesn't have E. And similarly for T2. And so altogether we get 1 plus 1 minus 1 is 1. Okay, so that does the induction step and finishes the lemma. Okay, good. So next time we will prove Euler's theorem and continue on from there.